Hi, everybody. So my name is Guy Margalit. I was the founder, co-founder of NooBaa, and which was acquired by Red Hat almost a year ago. And with me, Nimrod Becker, the engineering manager at Red Hat and the R&D manager for NooBaa before. And today we are going to present the NooBaa deep dive, the first session of NooBaa. It's going to focus on what is NooBaa, what is it good for, the architecture and product, and also show you a demo of how the product looks like, what's the content of the features that it has, and some design considerations that we heard were interesting. At the end, you can add more questions if you want to ask about why we chose something or what we do exactly for some specific technology or feature. Okay. So to begin with, I just want to throw at you just what NooBaa does. So NooBaa does what we call native multi-cloud object storage. So we're focused on objects. That's one piece of the title, and we're focused on cloud, which can be private cloud as well, but we're focused on cloud. So cloud native is what you can see in that, and multi-cloud is what we provide in that ecosystem. So in order to tackle this problem, we sort of took the approach of splitting the problem to three, as everything else. So the top sort of layer is just to provide applications with an object storage interface. S3 is the de facto standard, so we're using that. We're also supporting Lambda. We'll get to that specifically later for specific use cases that we found. So that's the top layer, the protocol, the endpoint service that we provide. The sort of bottom layer is connecting to any type of backing store. It can be public cloud, private cloud, through APIs or through just connecting to volumes. So putting a file system on top of a volume, using that as storage. Right, so we take any type of storage, AWS, Azure, Google, or volumes, we attach that to our system, and we represent that as storage for our objects. And the middle layer is the policies, and that's what where we provide multi-cloud capabilities such as mirroring, tiering, namespace, which we'll discuss a bit later. Function triggers is the Lambda piece that we'll describe, and efficiency in storage, deloop compression, encryption, etc. So all the policies that bridge between the application APIs and the backing stores that are connected to the system. So that's the overview. And now I just want to sort of touch on a few points that we focused on just to sort of explain where we come from, because you can do an object store in many different ways. You don't have to do it in a multi-cloud fashion. You can choose to focus on low latency, for example. You can choose to focus on small files. You can do a lot of different focuses, but some of them make more sense than others. So what we focused on from the beginning was user experience. Our first hire was a UX person, for example, as a startup. So that we started that. We have a UI that allows discovering the features, going through every piece of the technology. So we represent the technology through a graphic interface to allow people to actually understand it as much as we can. So that's one point. Containerization, so we didn't come from that, but as we joined Red Hat, we made a complete shift of the product to be containerized. So now it's fully containerized in Kubernetes and Openshift. So that's the second point here. In terms of workloads, so some workloads can be different than these, but for our cases, we typically looked at large objects, high throughput. That's the focus for us in the workloads world. So these are just examples, but just to give you a sense of what it is and what it is not. And the last point is, just to explain that, it's optimized for bandwidth, so high throughput, and not low latency. So since we want to provide multi-cloud capabilities, we're not going to optimize IOs just for low latency, since we're going to cross geos just for storing, mirroring data, etc. So it doesn't really make sense to optimize the entire system for low latency and then cross the ocean with your networking. So we prefer to focus on throughput. Okay, so this is the high-level overview of where we come from and what we want to do. And so sometimes we present a demo at this point, but we do prefer in this context to show a little bit of architecture, describe some design points, and then Nimrod will cover the demo in the product. So I know it might be difficult at this point to jump into the architecture, but let's try. If it's not going to work, it would be helpful if you tell me at the end. Okay, so this is just a graphical slide that describes the system and the three layers that I described. So the S3 API is here in the front, facing the applications. In the back end, you can see backing stores of different types, right? Can be on-prem, can be different technologies, anything consumable through either the cloud API, such as S3, Azure Blob, Google Cloud Storage, and or just plain drives using volumes and file systems on top. And in the middle, these are just examples of how we of use cases. Let's say multi-cloud buckets, so taking a bucket and spreading it or mirroring it over multiple clouds. Hybrid is just the same with on-prem. Multi-site bucket is between two data centers, right? And one thing to explain here is that all of these policies are can be dynamically changed. So it from the get-go, our assumption was that nobody really knows where the data should end on, right? You can tell where you want to start, but you might need to change over time. And this is why everything, like all these policies, when you just click them and change them, we actually go in the background and move the data, apply the new policy, and the system is completely dynamic. So it's not, you don't configure the system and just deliver that configuration and it's fixed forever. It's completely flexible and dynamic for the administrators, of course, not the applications. Applications are agnostic to that. They just see the endpoint, of course.
Can you give an example of what do you mean by configuration here?
Yeah, so for example, you can, so we'll show it easier on the demo on the system itself, but one simple example, you start on-prem, right? So you store your data on-prem, you add the cloud, you mirror to the cloud, and at some point you just remove on-prem, get to the cloud completely, right? So you can make all these transitions and it's from the same system without changing your application, protocols, or your deployment. Okay, that's the easy examples. You can decloud, you can go to the cloud, or you can stay in a mirrored or tiering fashion, which is more complex, but sometimes necessary. Okay. Okay, this is the Mona Lisa. It sort of, this tries to illustrate what we do when we ingest data. So I'm just going to go over it and give you some annotations on each of these pipeline stages of how we ingest data to the system. And hopefully it will help you to understand how the system then looks like when the data is inside. So writing an object such as the Mona Lisa to NooBaa would start from fragmenting the object to pieces. We do that in order to achieve, first of all, IO, just splitting IOs into fixed or not fixed, but somewhat fixed chunks. And handling these chunks is easier than just blobs of gigabytes or terabytes. And so that's one piece of it. But the other is also for dedupe. So we want to create a dedupe context. We fragment based on variable size dedupe content-based chunking, which is it can be several things. We use ravine chunking, and we average at 4 megabyte chunks. So it's a large chunk system. If you are coming from other storage subsystems, this is quite a large chunk. So that's one. Here you see the pieces look roughly the same. In reality, they have a minimum and a maximum size, so it's between these two, in the range of these sizes. So that's fragmenting. Deduplication, we have a dictionary of these chunks, of the SHAs of these chunks, the hashes, and we look up and we can tell you that the face of the Mona Lisa is exactly the same as their chest. You can dedupe that, which is, of course, irrelevant. And next step is taking each of the chunks that were not deduped and compress them. Of course, images are not that compressible, but still. We use, in this case, snappy compression by default, just because it's fast, but it's pluggable, so we only plugged snappy and zlib so far, but we can plug more. And then we go and encrypt these chunks with a random key per chunk, and we use AES-256 and save the keys as a metadata for our metadata in our metadata system. And eventually we take each of these chunks and apply the placement policy on top of them. So if the policy means store 3 replicas in these volumes, or in this volume group, then we do what you see here, like 3 of the red, 3 of the black, 3 of the gray. And it can also be applied to mirroring between data centers, clouds, etc. So London, New York, Paris. So depending on the policy, we store these chunks. I didn't mention we also support erasure coding with any kind of Reed-Solomon numbers, but so we sort of packed in all the efficiencies of storage that you can imagine in this set. And this, eventually, what we have is encrypted chunks on clouds or data centers. So nobody can actually go into these machines and read because the keys are not there. The keys are separated to the metadata server, and I'll discuss that in a second. And so you can store your data on the cloud, but not expose the data to the cloud infrastructure or platforms. Okay.
Did you say over what you dedupe? Do you dedupe over just data in a single bucket container, whatever you call it, or do you do it across the?
Yes, thank you. So the context of dedupe is a bucket, and it's actually the reason. So we had a few versions of it, but the reason was that we wanted to support bucket policies which are distinct. And if we dedupe across buckets, we also needed to apply to sort of merge the bucket policies between these. And we decided that for simplicity, it's better to probably respect the bucket policies better than the dedupe, the global dedupe. So we chose to use a bucket, a dedupe per bucket.
Okay, thank you.
Okay, so the components, this is a view of the components of the system. I'm going to show you how the data path works, how the control path works, and talk a little bit about scalability of these different components. So we have the application right here on top connecting to an endpoint. The endpoint communicates with what we call a brain or a noobaa-core, and this component is storing all the metadata of the system and sends back instructions to the endpoint where to write the data to. So the endpoint does all the heavy lifting, chunking, dedupe, compression, encryption, sends metadata to the brain, gets instructions back, where should I write this data, how many copies, how many, what's the policy of that specific bucket that should be applied. And at the endpoint, writes the data out either to API consumable storage, cloud resources as we refer to it, of any of these types, or to our storage nodes, which represent a volume, basically, which we store chunks in that. And the difference between them is we typically refer to cloud resources as resilient, so internally resilient, and we don't create replicas inside the same resource because it typically doesn't make much sense. These resources typically create their own replicas internally, or resiliency, whatever, how they do it. But for the storage nodes, we apply erasure coding or replicas depending on the policy. So that is where we bring the implementation of the resiliency policy. And these, for storage nodes, we also, and also cloud resources, we actually monitor the resource itself. So we monitor that we have connectivity. For example, if it's AWS, Azure, Google, we have connectivity to the cloud. And if we, if the connectivity drops, we mark it as that backing store is not available now. We can serve from the, if we have mirroring, we can serve from the other one, for example, right? So we have all the capability to detect failures and recover immediately using another copy or erasure coding for reads, of course. That is the data path. So the scalability is based on, so cloud is typically scalable on its own, so on its own technologies. On our side, we have the endpoints as stateless. So they don't require any information other than the control path communication to the noobaa-core. And so we can scale them up as much as needed and scale down. It's completely flexible. So we can tap and use more CPUs, more memory, more network interfaces, more nodes to serve application workloads. And the data path goes out directly from that endpoint, so that that provides the scalability of all of the above, the CPU, memory, and network. On the storage nodes, same thing. So we can create multiple of these. We only thing we need to do is monitor them, their state, and rebuild if any of these become offline or unavailable. And the core is the last piece. It's so unlike the rest of the workload that we're serving, the core actually represents a structured workload, a database workload, and therefore we use the database internally to storing the metadata of where the objects are stored, which nodes, or which resources each of the data, every portion of the data is stored on. So we have all the information indexed and ready to be used inside the core database. And that database is, as we'll explain later, is a MongoDB database. It's NoSQL, and it's designed to be highly available and scalable, so that we can have replicas of that database and have high availability and charting, of course, from that point of view. And so that design keeps all these pieces scalable, each for its own specific use case. So endpoints, completely stateless. The core is a stateful database, NoSQL, and the storage nodes are unreliable drives that we use with replicas of erasure coding.
Basically, it seems like if you have a limit to the scalability, it will come from the core. That's the only one that has have some consistency.
Well, so the others are, let's say, the endpoint is the least limiting factor, right? You can add as many as you need. The two others, so storage nodes, right? If you have a lot of them, you also need to monitor more of them. You have more failures to handle, right? So that's also sometimes limiting. And the core is basically the same solution as you see in databases, right? You scale it out using sharding, and that's your main tool for scalability. It's limited in reality, of course. You don't get to limitless sharding clusters, but that's the main tool that we picked on in order to implement that capabilities.
What are the chunks that you're storing in the storage nodes?
So the encrypted chunks. The encrypted chunks that, if we go back here, so these one of these would, so each one of these will end up in a storage node. If we wanted to use drives, so volumes, volumes, we put a file system on top, put a storage daemon, right, an agent that would handle that file system and drive, and we write files to that.
Okay, maybe I got something wrong. I thought I heard you saying that the storage nodes are unreliable storage.
Yes, we treat them as unreliable, yeah.
Oh, okay, so you enable reliability by having the erasure coding and being
on top of them, exactly.
We assume that you might want to use that because you have unreliable storage and you want to provide that to the system. So we implemented resiliency policies. We'll show it in the product itself. You can turn it on and off depending on the...
However, this is also configurable, so if you know, that you're using a volume on top of a resilient system, you can configure the bucket to lower replicas or to disable erasure recording if you, as an admin, have the knowledge that the system underlying is reliable.
And the reason why you have the storage is in case that the user does not want to use the public cloud-based storage or has their own storage that they ask you to use, for example, local on-premise cost.
I think for once, this was the default that many people just went to, right? At some point, cloud became as popular as that, but in many cases, this is still a default because you deploy NooBaa in some infrastructure, and then you have some storage in that infrastructure, and in many cases, you just want to, let's start. Okay, I have infrastructure, let's connect it, let's use it, and then we'll see. If you want to go to the cloud, let's go to the cloud. If you don't want to go there, we don't.
Yeah, adding to that, if you think about Kubernetes, then usually we only give you the object flow, right? You will usually have something that gives you block and file for PVCs and PVs. So we can also use that if the admin wants, because he already has something in place, we can use that as storage as well. It's also the other side of what Guy just said.
Okay. I don't think I want to say much more on that slide, but I do have a similar slide just to add to the scalability piece. So I made this actually today just because I'm not sure you'll be interested. I'm just going to go over how we created this as a efficient, perhaps, technology. So we took technologies that made sense for the workloads that we want to serve. So we took as a base for the endpoint Node.js and also the rest, by the way. But Node.js has a very nice property. It's it's behaving very well in I/O concurrency. So it has a async loop. It works very well for I/O. So Node.js bundles OpenSSL. That is doing all the TLS, SSL, and encryptions and all the functions that we needed for creating a secure private, encrypting the chunks, etc. And still, Node.js, while it's very well doing things very good for what it does, when you actually want to do a pipeline of dedupe, Rabin chunking, and compression, if you want to do all that, one of the things that Node.js doesn't do well, it doesn't have multi-core threads and stuff like that. So what we did and what is extended had an add-on to Node.js, which we wrote native. So it's taking OpenSSL functions, doing everything natively to do all the pipelines for dedupe, compression, encryption, right? So that uses the Intel Storage Acceleration Library for doing erasure coding, for example, and compression, decompression. I think that's a snappy logo somewhere on the top here. So all this is sort of running in a multi-core, like more threads that Node.js doesn't block its own event loop. So that's the basic That's the core of the endpoint technology, I guess. And these technologies are also being used in the noobaa-core and the storage nodes, some subset of it, of course, because we don't need all of them in every place, but this is what provides us with a high efficiency of these components. Okay, so I'm done with architecture. I'm going to hand off to Nimrod, and you can tell me next slide,
yeah,
or if you want to.
Next slide. Okay, so I want to jump a little bit into demo, into showing you the system, showing you a bit of what Guy said. Yeah, I'm going to need what Guy said, and then I'll talk about a few more features that extend to what we talked about. Slides. Let's see if it works this way. If it won't, then I'll use your method too. Okay, so this is the noobaa system. Like Guy said, we had ease of use in mind, so we built it with a way for an admin to come in, doesn't have to know anything, and can discover on himself what we offer and what are the capabilities. And I want to jump and talk about the things that Guy mentioned. So I'll start with the backing stores, with the resources. So just as an example, in this system I have configured an Azure resource, which sits on a certain blob, a Google Cloud resource.
Can you increase the font, please?
Yeah, I can zoom in the browser, not increase the font, but that should be good enough. I have a local volume-based resource, which has 3 PVs attached to it, 3 agents with PVs attached to it, and I have an AWS backing store as well. I can go in, I can see the different metrics that we collect, analytics that help me understand why I'm paying so much at the end of the month, or other stuff like if I'm using local volumes, what's my capacity when I'm going to run out and stuff like that, and also the state, like I said, if something is disconnected, an automatic rebuild policy will trigger, and that's the resource part. On the bucket part, which is basically the logical part of the system, we have different buckets and different policies. And as you can see, when I'm going into a bucket, I can configure the tiering policy. Per each tier, I can configure what Guy mentioned as mirroring. So I can choose out of all the resources I defined what is the policy for that specific tier, because I can have a single resource on my first tier and then a mirror between 2 clouds on my second, for example. So each tier has its own policy. Resiliency policies and other stuff that Guy mentioned, like replicas and erasure coding, also configurable, quota, and basically stuff that you expect from an object or a storage system. Something that we talked about was Lambda, and in here you can also see that you can connect triggers to a certain bucket, and you can have data-driven flows like creating new objects, deleting objects, and we even added read for a specific use case that I'll show later. And you can decide for each type of event what kind of a function you want to run. Obviously, you can set certain prefixes or suffixes, so you can be more like everything under a specific prefix folder would create would call a certain function, something else would call a different function. On the buckets, we also have something which is called namespace buckets. I'm going to show a slide about it. It's something different. It's not using the pipeline that Guy described, but I will talk about it a bit later. And the last thing I wanted to show is basically that we have, for each bucket and for each resource, we have something we call region, which can be set by the admin. And this gives us a locality awareness. So if a certain endpoint is at region A, and the policy of the bucket is mirroring between region A between a resource, which is also defined on region A, and region B, then we would serve reads and writes from region A to that endpoint. And if a second endpoint comes up and it's on region B, we can also serve reads and writes local to that region. So as long as there is an endpoint and a policy that corresponds to that region of the endpoint, we can serve locally, which is important when you talk about multi-cloud and crossing the ocean and stuff like that. We have more stuff in the UI, which I won't go into. Stuff that you can expect, like configuration and accounts and restriction on accounts, which buckets, which IPs, normal stuff, right? A section for analytics.
Maybe just the egress.
Yeah. So, for example, I don't think the system has written anything, so I don't think the graph would be very interesting. But we try to have some interesting insights into your data, like estimating how much egress you have, so you would know what to expect when you come to pay the bills at the end of the month. That's about it, and I'll jump back to the presentation. So we talked a little bit about functions and triggers, and we added that midway into the development of the system, and I wanted to talk to say why we added that, and we saw basically two flows. We saw data-driven flows, so we always use anonymization as an example. Let's say you have logs containing health records or credit card numbers, and you want to do like a masking. You upload the log, you have a function that goes over and masks all the sensitive data, and then you can just run your analytics on the log. So that's one type of flow. And the second one, which we actually had customers using it, is admin-driven flows. So, for example, a customer who was an MSP and provided storage and services to its own customers, used the Lambda to create its own automatic flows. So it would create a user with access, with bucket, with resources, all in a single command in order to, well, make his life easier instead of having create each of these config objects on his own. Okay, so I mentioned namespace buckets, and we started this feature because we thought about lazy migration, but this feature can help in other places as well. Basically, the idea is you come to a customer, and the customer already has a big data set, something that is not easily copyable between locations. You would not expect the customer to copy, I don't know, 100 petabytes of data from AWS to Azure, but he wishes to slowly move to Azure. So a namespace bucket would allow him to connect NooBaa to the current buckets on AWS, for example, that he is using, and start serving from there. He can then add a target write resource to Azure, which means that any new data which will be written to Azure, while the system will continue to serve all data from AWS. So over time, all the new data would migrate to Azure, but he will not pay not the ingress and not the time that he will need to now stop everything and wait until all the data is copied. In this mode, we do not chunk, encrypt, and compress the data. The data is saved plain as it comes from the application. And basically, if I remember correctly, Microsoft was interested in it because they wanted to help people move from AWS to Azure and have their insights run on the data. So the saving the data plain and not chunked was also part of the requirement.
But in many cases, we also layered namespace buckets on top of the normal buckets.
Yeah. So basically, the target can be even a NooBaa bucket, in which case you create your old data repository which you serve from, but when you start writing new data, you do use all the capabilities of NooBaa because you write to a NooBaa bucket, which then sits on top of whatever resources. Yeah. So that's the namespace feature. And I know there were some questions about noobaa's metadata and Mongo and how do we use it. So I'll do it quickly. So there are 3 types of metadata that noobaa keeps: configuration objects, all the policies, accounts, keys, stuff like that. The objects metadata, which is the mappings of the parts, the customer metadata, and the encryption keys, and the analytics and statistics that we save for all the other objects and configurations in the system. Now, the handling metadata is a structured problem, even though the data itself is unstructured, and so we chose to go with a DB. When we chose the DB, we thought about few things that we need and we want from the solution that we are going to use. One of them was compound indexes. We wanted to use this in order to have us, the noobaa system, easier to, let's say, okay, I'll go with an example. So for example, when we implemented the S3 versioning part, because we had a DB that supported compound indexes, we could just put and offload all the work of the versioning onto the DB, and we didn't need to do a lot on our side. We wanted something that have performance and scalability, high availability, and usually those 2 requirements go with eventually consistent, usually. We wanted a DB which is schemaless, because it helps us be agile, be fast. It shortens development times because we don't need to worry about, okay, how do we upgrade the schema? And of course, we wanted a solution which is popular because you want support and stuff to advance. And so when we looked at all of these and we compared all the NoSQL DBs, MongoDB was the winner. And we chose MongoDB. It answers all of these. It has its own high availability and sharding mechanisms that we simply use. It is eventually consistent. It is schemaless, and it also supports compound indexes. And I think up to now it's still the most popular one. I hope it was fast enough and I'm on time. So we'd be happy to take any questions. One by one, though.
Okay. With the namespace bucket, you go and you read from the old storage, the AWS S3 in your example. If there's a GET request for data and it's not in AWS, you then check in the new location in Azure.
Yeah. So a namespace can have multiple read locations, not just one, but currently a single write and multiple reads. And yeah, we're gonna check and serve you the latest one. If it doesn't exist on one of the resources, obviously you would get from where it does, and if it's not existing anywhere, you would get an error. Okay. But yeah, you would get it from the place that it resides and the latest version of it.
Okay, and the write policy is always to the old. You don't do a migration on the fly, like for example.
No, the write policy is always to the right resource, to the single write location. By the way, we added to that flow a lambda if you wanted to do like migrate on write, so you can just delete when a new object is created, and you can just call the trigger on a function and delete the old one, so you can actually move the data. Cool.
Basically, other cases where you have to actually go to the cloud and find out if something is there, or the core knows.
So in namespace, we don't keep the metadata because we don't keep the mappings of the objects. We don't chunk them, and okay. We don't have the knowledge. Regular data buckets, which we chunk and dedupe and encrypt, we do know where everything is.
So for namespace, you'll actually have to go to the first place, try it out. If it's not there, go to the second.
Yeah. Yes.
We have some caching, but in the endpoint, but it's not for the purpose of indexing the entire data set.
It seems now the namespace and the data buckets are totally different products. here.
They are.
Why don't you combine it some? I heard about the Microsoft and the requirements, but you can have another version of it that do combine it, and you have this single namespace, but you're still doing the fragmenting, etc.
So actually, it's actually a great point. Technically speaking, they are the same element in the system. Every bucket in our internal representation has a namespace policy and a tiering policy, so that you can have both a namespace and a tiering in the same view. But for when we tried it out on our UX person, she said no. You can't understand this type of resource is very different than this type of resource. It's really hard to explain. So we ended up doing that mostly in the representation to the for administrator. However, looking forward, if we take that into operators, and we'll talk in the next session on how we integrate into Kubernetes, in these cases we might create policies which already come ready to use, right? Because in many cases in Kubernetes, it's not like you use the UI for ticking and setting things. You create your configuration as code and you deploy that thing, so you have less room for becoming confused about if the UI is clear enough, what's the piece of that. You actually have a configuration, you just deploy it. So it might make sense that you have a single bucket that has, okay, I'm going to read from that remote bucket in AWS as a first option. If not, I'm going to store locally in the current bucket the tiering policy, which is 2 tiers, mirroring, etc. So I hope that answers the question. The UI was chosen not to mix these two animals together.
For the multi-cloud variety, a user said can add a new cloud target, right?
Yeah.
The right term, target?
Yeah. Cloud connection.
Do you then do some kind of a reorg of the data? I'm assuming not.
No. You mean in
for the tiering purposes, for the chunking?
Okay. So tiering for us is like a greenfield, right? We take a bucket in the cloud, but use it as a storage target only for the data that we put inside. We don't look at the rest. Right? It can be a bucket that has a bunch of other things. We just decouple from that. Okay. For namespace, we actually look at the bucket and say what is there. We represent that. But for data bucket and tiering policy and all that, we just use it as a storage target. Is that what you were asking?
That was the first part. The second part was for chunking. My understanding might be wrong, but you generate multiple. You take an object that the user wants to upload, and you chunk it, and then you store it. And if you have multiple targets, then you store the chunks across the different targets, right?
Yeah. Okay. Let's say we have mirroring between Azure and Google. We store each chunk in both. It's async mirroring.
Okay, I think I'm going to answer my own question. And then you're able to identify where the chunks are using the MongoDB. So if there's a new target, the chunks are not there.
So yeah, if we add, for example, now we go to UI, we add, okay, so I want another copy on, if you can actually show it, it might be easier to see. When you actually add a mirror, we immediately represent in the UI a placeholder for that new location, and the database doesn't have it yet, right? Yeah. But once we actually replicate the chunk from one cloud to the other, we'll also have representation in the database of one entity that represents that chunk in that new location.
Yes, so I'm just adding a third mirror group, and if I go to an object within this bucket, well, obviously, demo effect always never fails to to deliver. Okay. Then you would see, okay, it was too fast, but you would see that a new target, a new replica was added on the Google one.
So if we were fast enough, we would see it as
yellow, being rebuilt into the new resource.
But this means like we have 3 locations, and we can query the database to say where do we have the locations, and if we want to use, let's say our endpoint is on AWS, and the region we said makes sense, then we can optimize and read that directly from the AWS one and not take another one which is far away and would cost us egress and latency, higher latency and time. Okay.
Any other questions? Okay. So thanks to the speakers.
Thank you very much.
Thank you.